Welcome back, everyone. Let's now switch gears to understanding how to actually implement support vector machines for classification with scikit-learn. As a quick note, we're going to be using a function call from an included .py file inside the support vector machine folder. This function will allow us to actually visually see the margins as well as the support vectors. Let's get started. I'm going to open up a new Jupyter notebook. Alright, here I am under the support vector machines folder. As I just noted, there is an svm margin plot.py file. If you click on this .py file and open it with Jupyter, you'll notice that it's actually directly from the documentation, and it essentially just is consisting of one function that says plot svm boundary that takes in a model, your x features, and then your y labels, and it will actually conveniently plot a scatter plot and then the decision function as well with the margin. And it's also going to highlight the support vectors. So we'll be using this plot svm boundary after we import svm margin plot.py. In order to import this, you should be running your notebook in the same location as this .py file. So I'm going to start a brand new notebook here, and we're going to follow along with svm classification. Alright, I'm going to begin by importing pandas as PD, and then we'll also be doing some visualization, so I'll import matplotlib.pyplot as PLT, and I will also import Seaborn as SNS. And just in case we need it later, I will also import NumPy as NP. The data we're going to be working with is essentially simulating a medical study in which a mouse is infected with a virus and then given various doses of two medicines, and they're measured out in milliliters, and then we check 2 weeks later to see if they're still infected. Let's explore what this data set looks like. We're going to say PD read CSV, and this is underneath the data folder. You have to actually go back up a directory to access the data folder, and then the name of the file is mouse viral study. So mouse, you should be able to tab autocomplete this. Okay, so we underneath the data folder have a mouse viral study.csv file. Run that, and you should then be able to see what we were just discussing. So we have the amount of medicine 1 in milliliters, amount of medicine 2 in milliliters, and then whether or not that mouse still had the virus present 2 weeks later. So let's now explore the actual classes themselves and the separation between its two. And a scatter plot would be a good way to do this. We're going to say SNS scatter plot. X is equal to, and the first column is called med_1_ milliliters. So we'll copy that, have that one along the x-axis. Y will be equal to the other column. So same thing, except instead of med1, it's med2. And then finally, we'll also say the hue is equal to whether the virus was present. So the virus present column. There we go. And finally, we have to say what the data source is. So data is equal to df. Run that, and you should see something that then looks like this. Clearly, we're dealing with this really nice example use case for a data set. There's only 2 features, and they're very separable. So what we want to do is start exploring a lot of the ideas we talked about, actually defining that separating hyperplane, and then seeing what happens when we explore different parameters and different kernels. What we're going to do is actually just manually plot out a hyperplane on this. So if you take a look at the data points themselves, if we get a line that is approximately something like y equals mx plus b with a b intercept of 11 and a slope of -1, that will actually separate this out. So what I mean by that is the following. I'm going to create right here a hyperplane, which recall in 2D that's really just a line. So we're going to say create a hyperplane, and it's going to be x is equal to np linspace. I'll go from 0 to 10 and 100 points there, because what I have here along my x-axis is essentially going from 0 to 10. So I'll say 0 to 10 and then give me 100 points. And the relationship I want to create is a relationship of y equals mx plus b. And through a little guess and check, nothing too crazy, you can see that if you have a slope of -1 and a beta coefficient of 11, recall that we already discussed the hyperplane equation where it could be a set of beta coefficients times the features. So I have something very similar to this, just a separating hyperplane, y equals mx plus b. Then I can say PLT plot, and I'm going to say plot x versus y, these x points versus the equation y equals mx plus b, essentially plotting a straight line, and I will have the color for that line be black. I run this, and if I put this all in the same cell and just say plt plot right after this scatter plot with all this defined, I should now be able to explore this separating hyperplane. Okay, so now what I want to do is really start to understand how support vector machines are able to figure out what is the best essential slope for this line and intercept for this line, at least in 2 dimensions, in order to separate out these classes. Obviously, we can begin to play around with the slope and see that there are actually quite a variety of lines that could separate out these classes. For example, if I say slope is equal to negative 1.1, run that, that still separates out the classes perfectly. However, you notice we're much closer now to the 1 grouping, and clearly we probably want something with a little more bias. Let's start exploring the support vector machine by saying from scikit-learn dot, and the family this is from is SVM for support vector machine, and then we're going to say import, and if you hit tab here, you'll notice that there's actually quite a few different things you can import, but the one we're going to be working with is SVC, which is the support vector classifier. And we know that the only thing we need to add to go from a support vector classifier to a full support vector machine is the addition of kernels, which we'll be able to see how that works later on. And I would encourage you to call help on SVC, the class object, and begin exploring the various parameters you can have here. The main ones are the C parameter. Recall, that is a regularization parameter we talked about. If you allow for misclassifications, then you can adjust the C parameter. You should also recall from our discussion that it's actually inversely proportional to the C value shown in the equations. So it's not just a higher C means more misclassifications, it's actually inversely proportional to that. You should also be able to see that there are a variety of kernel strings we'll be able to provide, and then, depending on the kernel, you may require an addition of a degree or an addition of the gamma. So lots of stuff to explore here with support vector machines. The other thing we're going to do is, in order to just explore this algorithm, I'm going to skip any scaling or even really a train test split, since we're essentially just visualizing this and seeing the different effects. So I will say y is equal to df virus present, and x is equal to df drop virus present along axis is equal to 1. So we're not doing a full project here of train test split and scaling. You should keep that in mind when you're starting to use support vector machines, that you would have to do some sort of cross-validation most likely, but we just want to visually explore what's happening here. So I'm going to create a model, and for this model, we're simply going to say support vector classifier, and then we have to state what is the actual kernel we're going to be using. If we go back to help SVC, run this, and then scroll down to where they actually begin talking about the kernels. So we have this C parameter that we talked about, but we also have the kernels themselves. We see we have the option of a linear kernel, a polynomial kernel, a radial basis function kernel, which is one of the most popular and one of the most powerful kernels, and then we also have sigmoid and precomputed. Because radial basis function actually tends to work the best right off the bat, by default it will use radial basis function if none is given. The thing to note here is that for radial basis function, you do have to begin to explore the gamma parameters. And there's actually a bunch of details in the documentation on how gamma is related to this radial basis function. Or you could check out the previous slides to see the direct relationship in that kernel definition. But we're going to scroll back down here, and let's just start off with a very simple kernel. We're going to do the linear kernel and then just choose some C value. So I'm going to zoom back in here, and I'm going to say kernel is equal to linear, C is equal to, and I'll choose a very large value of C, 1000. Recall that for this particular C inside of scikit-learn, it's inversely proportional. So then I take my model, and just as we always do, we just fit it to my X features and my Y labels. Didn't really do a train test split just because I want to visually explore this and how it fits with all the data. Now that I have this fitted model on my X and Y, I can actually import from SVM margin plot, and recall this SVM margin plot, this is this custom .py file. This is not included within scikit-learn. You need to make sure that you're in the same location as this .py file that we created for you. And then from SVM margin plot, import plot SVM boundary. You should be able to tab autocomplete that if you are in the correct directory. So run that and then call plot SVM boundary, and this will really help you understand the effects you can change with support vector machines. So I'm going to pass in the model, pass in my x features, pass in my y label. And when you run this, it's going to go ahead and actually plot out the hyperplane, the margins, and the support vectors. So notice with a linear set hyperplanes, all it's saying is just find a linear line and then expand the margins until you actually begin to hit the support vectors. So this was with a very high C value. What we're going to do in part 2 is explore the variety of kernels available to us, as well as the different arguments that each of those kernels takes. So you should be able to, at the end of this lecture, begin to plot this support vector machine boundary with a fitted model against the features and label. And then in part 2, we're going to explore the variety of hyperparameters that we've already talked about in theory, but we haven't actually explored yet with scikit-learn. I'll see you at the next lecture.